Today class we will discuss axial deformation, something that we talked in even the first lesson, and we also study stress concentration and area moment of inertia. And the last class we deal with the material properties, and we have different phases when we draw the normal stress and normal strain curve. And today we start with the lesson with the modeling the performance of the material with the elastoplastic behavior. And just get back to the note we have in the previous lesson when we draw the normal stress and normal strain curve. As you can see, for a certain material, we have an elastic region and then plastic, and then with including yielding, strain hardening, necking, and the stress increasing until the ultimate stress or ultimate stress, sigma ultimate. So with that actual behavior, today to solve the problem, we will model that with elastoplastic behavior. So what is that about? So basically to modeling the performance of the material, modeling performance. So with the diagram that the curve that we have for normal strain and normal stress, and for the material I just showed you earlier that we have in the previous lesson, they start with the linear motion, proportional limit, then they start move to the yielding, and then it will increase the stress. Then the strain still increase, and at some point without increasing, the strain is still increasing, and then the material rupture. So from that, as you can see, with that behavior, there are two phases, elastic and plastic. And now when we model with the elastoplastic behavior of the material in the red line, then during the elastic we model exactly the same with the real curve epsilon and sigma. And then when it go to yielding and in plastic region, we just assume it about horizontal. So it's purely 100% elastic in the first phase, and then 100% plastic in the second phase. So whatever that here is the sigma that we want to design for, and that red one, we call it the elastic and perfectly elastic and perfectly plastic. So either elastic, very first replicate the real material, and then the second phase it combined between elastic and plastic, but we assume it perfectly plastic, so it's the line go horizontal in there. So that what we call elastoplastic behavior. And as you can see, with that we are more conservative with regard to the stress, because as you can see the red line below the actual performance of the material, the sigma ultimate, it go up here, while we only have in the point like there. So it's more conservative. So, and that's good for our design when we consider that at a additional factor of safety in there. So elastoplastic behavior is a conservative assumptions with regard to stress. Assumption with regard to stress. And I show you the actual ultimate stress in here, sigma ultimate, and the one that we designed somewhere there. So it's really conservative for elastoplastic behavior. So from that we can continue with the topic is the axial deformation. And that a change in length of the cowl member. And when we have a deformation, if you recall, that is delta. So let's see a cowl member in here. And for that cowl member, as you can see, the original is the dash black line, that original member. And now if we have a force P applied on that cowl member, the member is increasing the length, so you can define the length at the original. If you recall that it is L0, and then the length at the final length, that we call that final length in here, that we call it we call the final length LF, final length. LF. And you also know the epsilon, which is the normal strain. In this case, normal strain in that member, it equal to delta over L0. And we also know delta, the deformation, it equal to final length minus original length L0 divided by L0. And with that, we have several assumptions to apply for this axial deformation. So assume what we have. So we assume the cross section are constant. So as you can show in here, this is the cross section in rectangle. So we assume constant cross section. And then we also say that the material is homogeneous. So same material throughout, homogeneous. And we also assume isotropic. If you recall, when we talk about the Poisson ratio, we also mention isotropic. It means same properties in all directions. So when you have those two assumptions, we have sigma equal to B over A. And you can say if it cross section is the transverse, then it's AT, right? And then we also have if it inelastic region, which is the first region for the behavior of the material, then we can have the Young modulus equal to sigma over epsilon, and that's what we have it last time, right? So here we have there, and we have if it one horizontal, then the vertical is epsilon in the elastic region. From that, we have the deformation for the axial load or the cowl member. Deformation and deformation, and we have that is delta, and delta equal to epsilon L naught in that equation here. And epsilon from elastic, we have E equals sigma over E here. So epsilon, it will be sigma over E. So from that, we can plug in sigma over E L naught. And if the material is homogeneous and isotropic, we have sigma equal to P over A. So we can plug that in that equation. So we can have the deformation for a cowl member with axial load P. So the deformation equal to the load proportional to the load, the length, original length, and divide by the areas of cross section and the Young modulus, and that we box. And this equation, if you recall, go back to lesson 1, we also have that one here. But that just try to confirm how to determine the actual deformation, the change in length when we have a member in have a load applied along with the longitudinal axis of that member or cowl member, centric axial loaded member. So in the next video, we will talk about the compatibility and consistencies when you solve the statically indeterminate structure. So that's something go beyond our knowledge in engineering mechanics before we go to solve the problem today.